A binary logistic regression example. In this example, we're going to predict diabetes using logistic regression. The prediction problem is a binary classification problem. That means that you only have two outputs for target variable. That means whether the patient has diabetes or not. So it's positive or negative, 1 or 0. That's why we call it binary. Do the following steps. Download the files, including the IPython files, the template file specifically, and open it up. And also download the diabetes.csv data file. Open the template file and follow along. Okay, let's start by importing the libraries that we need. We need the typical libraries. NumPy, for example, pandas, and matplotlib pyplot. Next, we need to import the data. This is assuming that you have already downloaded the diabetes CSV file and put it in your directory or folder, the same folder that your this code, the template code is, or you have uploaded in your Jupyter directly. So I'm going to use the read_CSV function from pandas to read the data. And I'm going to put it in my diabetes data. All right. Let's take a look at the header of the file to see how does it look like. So this is the first 5 instances or samples of the data. We have pregnancies column, glucose, blood pressure, skin thickness, insulin, BMI, the DPF, age, and outcome. Outcome, the last column actually is the label here, the dependent variable, the target variable. 1 means that the person has diabetes and 0 means no, he doesn't. Okay. So next we want to select features and target variable here. So this means that it split our data into independent variables and dependent variable. So the first thing that I want to do is want to make it a little bit neater. We have too much, there are too much letters here, too much lengthy names for this column. So I have already make it concise and compact. Pregnancies, glucose, BP for blood pressure, skin instead of skin thickness, insulin, BMI, DPF instead of the diabetes pedigree function, age, and instead of outcome I have the label. So we're going to actually read the data again. This is just for neatness. We don't have to do this really. So I'm going to read the data again with these new column names. So see how we actually do this. I'm going to use the same data set, of course, and then I'm going to make the header equal to 0, so it won't actually read this header that it already exists here. And instead I'm going to use the names parameter and make it equal to the one that we have defined here, column names. So this is going to read the data with the get rid of this header here and replace it with this new header. Right, we can actually now, let's take a look at the header here. Okay, so this is our, as you see here, is much more concise. We have the pregnancies, glucose, body pressure, skin insulin, BMI, DPF, age, and label. So that's 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we have 9 here, but this is much more concise and smaller than the previous one. Now we want to split our data into feature variables, independent variable x, and the target variable y. So let's do that. So one way to do that, we can actually define a list here. I want to include all of these column label features here, all the features here, and I'll put it in this list here. And then I'm going to set that x would be my diabetes for all these feature names. So that would be features, and y would be the last one, the label here, label. So that would be label, and that works. Another way would be to use the ilog function. So ilog, I want all the instances of data, that means all the samples. So I'm going to have all the rows here, and for columns I want to have every column except the last one, which is -1, right? So I want to have it until -1. And y, for y we can say my diabetes ilog, again every sample and then only the last column, and this also works. Okay, we only need to do one of these. Okay, all right, so we already took a look at the my diabetes head, so we are good here. All right, now let's train our data into, split our data into training data set and test data set. Before that, we need to import the train test split function. So from I'm going to give it a nickname to make it easier to use it later. And then I'm going to put everything, split everything into test and train. All right, so by default, 75% are used for training and 25% for testing. We can actually change that by the test size here using the test size parameter. So I'm going to use 20% for testing, and I'm going to use the random state, so all of us would get the same output. Random states, for example, 0. There are different random states that you can use. Right, so now we can go ahead and develop our model. So from a Scikit-Learn linear model, this is the module where linear regression, the logistic regression exists. Import logistic regression. L and R are capital here. So after that, we're going to instantiate the model using the default parameters, and we're gonna make actually a copy of this. So I'm gonna call it my logistic regression, my LR, and that's a copy of logistic regression. And we're not going to set up any parameter, so it's going to be by default all the parameters that it's already set. And now we can actually train our model. So my linear regression model, my logistic regression model, fit it into our training data set. Right, now the model is trained. This means that, remember the odds ratio, the logarithmic odds ratio. So in that equation, all the coefficients b0, b1, b2, etc., all of them actually have been now set up. So our model is trained, it's time to use our model for prediction. So we're going to do that. I'm going to ask my model to make a prediction on the test data set. And let's also do that for the training data set as well. It's a spelling. All right, so now we want to see the accuracy score, the performance of our model. So first we need to import the accuracy score here. Okay, so from Scikit-Learn, the metrics module, we want to import the accuracy score. And now we can print out the accuracies here. On test data, now I'm going to give it the actual value and the predicted value. And also similar for the training data set. The actual value and the predicted value. So the accuracy score for the test data set is about 82%, and for the training data is about 76%. That's actually very good. First of all, it's very high. That's because our data actually is a standard. It's not just a random data. And second of all is that we don't have to worry about the overfitting problem, because the accuracy score on the training data set is not higher than the testing data. It's actually the reverse. Our model is doing better on the test data than it does on the training data. So that's very promising. Multi-class logistic regression, or the application of logistic regression for multi-class classification. We have already learned how a logistic regression model works in binary classification problems in which we have only two classes, class 1 and class 0, or positive and negative. Interestingly, we can actually extend the application of logistic regression for multi-class classification problems. One of the methods that is popular to use is called one versus the rest. Let's see how this method works. So suppose that we have k classes, k different classes. For each of these classes, we're going to actually train a different logistic regression in which that specific class is considered class 1 and all the rest of the classes are considered class 0. Then we're going to do it for the next class and so on and so forth until we covered all of the classes. So each class is going to have their own specific logistic regression tuned and trained for them. And after that, for any new data points that we want to make a prediction for, we're going to predict it actually as the class that it's going to give us the highest probability. All right, so let's see actually how this would work in using a simple example. Suppose that we have three classes here. We have the triangle, the crosses, and we have the squares here. And we have only two features here. So but the first thing that we're going to do, we're going to give this in nominal classes. So for example, 1, 2, 3. Doesn't matter which class is considered 1 or 2 or 3. Right? So here we have 3 classes, so we need to have 3 logistic regression model. So the first one, we consider the class 1, the triangles as class 1, and the crosses and the squares, or the class 2 and class 3, as the 0 class. And we're going to train the logistic regression at f1 of x, because f1 because it's actually trained for the first class. So as you see here, we only have 2 classes here. We have the triangle, or class 1, and we have the circles here, or the class 0. Right? So this is a binary classification problem, a typical problem that logistic regression is actually good at solving. So now we're going to go to the second class, class 2, or the crosses here. So we're going to do the same for them. And we're going to train a specific logistic regression for the class 2. I'm going to show it for f2 of x. And similarly, we're going to do it for the third class, the squares, with its own specific logistic regression model. Now, our model actually is a set of logistic regression. And when we have a new data points to classify, we're going to actually classify to a class that the probability of belonging to that class using these different logistic regressions is the highest. So f superscript I of x would be the probability that y belongs to class I given the data point that we have. And we're going to classify to class I if the class I gives us the maximum probability here. A multinomial logistic regression example. So now we want to see the application of logistic regression on a multi-class classification problem. In this example, we are going to build a logistic regression model to the iris dataset that we have seen before, where there are 3 classes or labels for the target variable. So please download the IPython template file and follow along. Happy coding. Start with the importing the libraries that we need. We need import NumPy and pandas for sure. And also, since we are working with the iris dataset, we need to import the datasets from Scikit-Learn. All right, now let's import the data iris datasets and put it into a data file name. So I'm going to call it data.dist. So that's going to call datasets and then load iris. So this is going to copy the iris dataset into a data. Let's take a look at the keys of this data file. Data keys. So we have target, description, the target names, feature names, data, and file name. Let's take a look at target names, for example. So we have Setosa, Versicolor, and Virginica. Let's take a look at the feature names. So we have 4 features here. We have the sepal lengths in centimeters, sepal widths, petal lengths, and petal widths. All right, so we are good to go. Let's go ahead and split our data into the feature variables x and the target variable y. So x is going to be our feature variable, and that's going to be the data. And to show you why is that, I'm going to go back again to the keys of this dictionary. So here we have the target names data. So data actually is all the feature variables, all those columns that include the feature variables, and target is just the target variable. That's why we can do that, right? Now, why would want be the target variable? So that's data target. Now that we have split our data into X variable, feature variables, and target variable, and let's actually continue with our model. So we need to first split our data into training and test data sets. So let's first import the split function. And then we're going to split our data into training and test. So by default, it's going to have 75% for training and 25% for test. We're going to leave it as it is, and then we're going to move it the random state. So every one of us would get the same output. Random state 0 here, for example. All right. So now our data is split. Usually it's a good idea, it's a good practice to normalize or scale your data before you apply your model or train your model. So specifically, this is true for specific models, regression models, and the logistic regression included. So let's go ahead and use the standard scaler to scale our data, normalize our data. First, we need to import it. It's in the pre-processing module. And then we're going to create our own copy of this. I'm going to call it my scaler. Then we're going to fit the scaler into our training data, the feature variables. We're never going to make sure that you never forget this. We're never going to scale our target variable. It's all about the feature variable. All right, okay, so let's actually scale feed our scaler. All right, and now we can transform our feature variable. So xtrain, I'm going to use the scaler to transform the train data and put it back to training. Same for the test data set as well. All right, so now our model is, our data is actually scaled. Now that we have split our data and normalize our data, we're going to go ahead and develop our model. So we need to import first the logistic regression from its module from Scikit-Learn. It's in the linear model module, linear model, import logistic regression. And now we're going to create a copy of that. I'm going to call it my logistic regression, my LR. And that's going to be a copy of the logistic regression. So logistic regression has a lot of parameters here. we're going to leave it as it is because it actually can detect whether you have a multiple class or you have just binary class, and then going to behave accordingly. So we're going to leave it as it is right now, and then we come back and play with the parameters. So we can actually train our algorithm in the same line. So let's do that using our training data. Okay, so our algorithm is ready, is good to go for making a prediction. So let's go ahead and make a prediction. And also we're going to make a prediction for the training data set. Okay, so let's go ahead and import the accuracy score. To see how is the performance of the algorithm. It's a metrics module. And now we're going to print out the result here. We're gonna do it the same for the test, the training data. So the accuracy on test data is about 82%, and on training data is about 91%. So as you see here, there about 10% or more a difference between. It seems that it's doing a better job. It has a higher accuracy on training data set than it is on the test set. So there is a concern about overfitting issue here. So now we can go back and play with the parameters to see if we can actually improve it. All right, so now we want to play around with the parameters of the logistic regression and investigate the impact. One of the parameters is called the multi-class parameter. The default value for that is actually auto, so it could actually automatically recognize whether you have a multi-class problem or a binary class problem. So let's go ahead and play around with this parameter. So one of the options that we have here is the one versus the other, or OVR, that we talked about it before, and the other one is multinomial. So let's go ahead and set it as multinomial. When we use multi-class classification multinomial, the logistic regression has to do regularization because it's going to create is going to actually make the model more complicated. So we have to be careful about overfitting here. So that's why it does regularization. And we have two types of regularization. We have L1 regularization, which actually uses the absolute value in the objective in the penalty function, as we saw it in the lasso regression, or it can use the squaring in the objective in the penalty function, as we saw it in the ridge regression. So that's called L2 type penalty. So to be able to actually, when is doing working on training data and figuring out the coefficients using the function, including the penalty function, it needs to actually solve an optimization problem. So it needs to use a solver, what is called as a solver, to solve the optimization problem. There is actually a couple of options that we have here. We have the default is LBFGS, and we also have the Newton CG. We have others that I can show you. So let's now go ahead and do set the solver to Newton CG. All right. We can also specify the random state here. We all of us would get actually the same output here. So let's go ahead and initiate the random state as 0. All right, so we are all good. Let's run this, and we're gonna run the next one. You have to run all the way down. So remember that before we change the parameters, the accuracy score for the test data is 82% almost, and for the training data is 91%. It's about 10%, less than 10% difference between two. So let's see what's gonna happen now. So as you see here, we see significant improvement in the both testing data set and training data set. And also the gap that there exists, 10% gap, is actually disappeared. So we no longer have the concern for overfitting issue here. And that's the power of working with the right parameter here. And so that's why we have a step in machine learning. It's called the third step, the optimization step, to tune your parameters or find the best value for your parameters. So there are a lot of other parameters here that you can work on. Also solver, you can use also OVR and other parameters. You can go actually to the Scikit-Learn website here. So this is the Scikit-Learn for the logistic regression. You see that here you actually can see the parameters for this. So it has the penalty L2 type as we have it in ridge regression, and we have other parameters here including random state solver here. The default is LBFGS and the maximum iteration that you want to run it. Multi-class auto, we have we talked about auto, we also used auto before, and as you see here, all other parameters here. And also you can see the discussion and description a little bit about these parameters in extent actually. So this is really a good source for you to use when you want to work on a problem. Right. Let's see the advantages of logistic regression algorithm. The logistic regression algorithm does not require high computation power, unlike the k-nearest neighbor algorithm that we have seen before. Also, logistic regression is actually easy to implement, as we saw in the example that we had. And it's easily interpretable. Also, it is used widely by data analysts and data scientists. It's one of the first thing to go to for classification problem, especially for binary classification problem. Let's now see the disadvantages of logistic regression. Logistic regression is not able to handle a large number of categorical features or variables. So if you have a problem that has a lot of categorical variables or feature variable, probably logistic regression is not going to perform well. Also, it is vulnerable to overfitting, and it will not perform well with independent variables that are not correlated to the dependent variable or target variable, and also are similar or correlated to each other.